Welcome back to Chem 4300. In this video, we're going to be continuing Chapter 8 on classical wave motion, and now we're going to turn our attention to something called the uncertainty principle. Now, in the previous video, we learned how a wave function can be localized. So, for example, I could take a rope and I could pull it tight and I can jerk my hand up and down and I can create a wave packet, this localized wave that travels across the medium, in this case, the rope. And we also learned that we can do a Fourier transform to decompose that wave packet into some linear combination of sinusoids. So what we found was that there was this region of space, this range of position, or I would say this delta x, describing the region where this wave packet existed, where we had non-zero amplitudes, that was associated with this range of wave numbers, which we found through the Fourier transform, that when those different sinusoids added up, they gave us the constructive interference to form this localized wave packet. So if we take delta x as our range of positions for our wave packet and delta k as the range of wave numbers that compose that wave packet, then the uncertainty principle tells us that the product of those two ranges, in other words, the uncertainty in position, the uncertainty and a wave number, together will be greater than or equal to 1/2. This is generally true for all wave functions, whether they're wave packets or not. And what we're going to do next is we're going to look at how we obtain this relationship in the case of, say, a Gaussian wave packet, where Gaussian is, of course, the special case where the Fourier transform of a Gaussian is another Gaussian. And it'll turn out that will be the case where we have the minimum uncertainty in terms of this product, delta x, delta k, will be equal to 1/2 in the case of a Gaussian wave packet. But generally speaking, that will be greater than 1/2 for all other wave functions. So let's take a look. So the first thing we need to address is how are we going to describe the position and the width of our wave function? We need some way to calculate from the wave function its position and its width, or say its standard deviation. And to do that, we're going to have to come up with some kind of probability distribution function that tells us, where the wave function is non-zero and where it is zero. So that's overall possible values of x. What are the regions where we have non-zero values of the wave function? Now you might be tempted to use the wave function as that probability density, but you realize pretty quickly that you can't do that because a wave function can be positive and negative, and probability densities can never be negative, so that won't work. But the wave function does have all the information we need to figure out where it is and what its width is if it's a wave packet. So what we're going to do is we're going to use the square of the wave function. So anytime you square something, you end up with something that's going to be positive, right? Always positive. And since we're sometimes going to be using complex forms for our wave functions, we're just going to go ahead and multiply it times its complex conjugate, which will make sure that we get not only a positive value, but we'll also get a real value. So generally speaking, that if we square the wave function or multiply times its complex conjugate, we will always get a positive and real quantity which can use as a starting point to obtain a probability density function. So the first step, making sure that we get something that's always positive that describes where the wave packet is here. But the next thing we need to do, of course, is to make sure that our probability density is normalized, so the area under that is 1. So what we're going to do is take our wave function and we're going to square it, and then we're going to divide it by the integral of the wave function squared over all possible values. That is our normalization factor. That's what we did learn earlier in the class. So the probability density that we're going to construct from our wave function is simply going to be 1 over our normalization factor times the wave function squared. Okay? And this is what we need to get our probability density. And once we have that, then we can calculate things, for example, like the mean position by just taking x times the probability density, integrating with all values, and we'll have the mean position. Okay, so that's the first step. So we're going to take this general definition that we learned earlier, and we're going to do it for wave functions by doing 1 over the normalization of the integral of x times the wave function squared. To get the packet width, well, what we're going to do is we're going to define the standard deviation as the square root of the mean of x squared minus the mean squared. So this expression, which you saw earlier, all we need to get from this is we already have x bar here. We need to get x squared bar, and we're going to get that with this expression here. Again, something we learned earlier in the class. And in this case, it's going to be 1 over n integral of x squared times the wave function squared. All right. So let's do that for the case of a Gaussian shaped wave packet. So if I take this as my form where there's some arbitrary amplitude A, and this is what my wave function looks like, and you can see here that at time t, it will be moving forward in time. But what I'm going to do is look at it at just time equals 0. So I'm going to take t equals 0, and I'm going to take this wave function, and I'm going to first create a probability distribution function from this wave function. So the first thing I need to do is to normalize it. So I'm going to take this guy at t equals 0, and I'm going to calculate its integral, so the wave function squared integrated, plugging this into here, you see you get this expression here, which then if I square that, and it ends up giving me this expression. And then going to an integral table, I see that this integral is equal to the square root of pi over a. You identify a as just 1 over sigma x squared. And so we get a normalization factor, which is a squared times the square root of pi sigma x squared. Okay. Next, what we're going to do is we're going to calculate the width of the packet. So we've already calculated in the previous slide, we already calculated the normalization factor. So now what we're going to calculate is the position first. And so we have our expression here for 1 over n x times this wave function squared. So this is x times the probability distribution function integrated, and that gives you this result here. Now, what you see is when you plug this guy, all this expression up here into here for time equals 0, you find right away that, well, x is an odd function, and this is an even function, and when you multiply an odd function times an even function, well, that product is an odd function. And when you integrate an odd function from minus infinity to infinity, you end up with 0. So we don't really have to do any work to know that that integral is going to be equal to 0. So that's out, and we see that our mean position is just 0. And that should be no surprise, because at time equals 0, this is just x squared over sigma x squared, and, times minus 1/2, and that's just a Gaussian that's centered on 0. So we knew that already, and we got exactly what we expected there. So now let's move on to calculating the mean of x squared, which again is just 1 over n x squared times the wave function squared. And that evaluates to this, and I'll leave it for you to do this. This will come out to be sigma x squared over 2. And if I take those two results for x bar and x squared bar, then plugging into my expression for the standard deviation, I get sigma x over the square root of 2. And that is our result for the width of the wave packet in space, in position. So what we've done then is we have a value that's in terms of the standard deviation of the wave function. So let's not get confused here. So x, delta x, is the standard deviation of the wave packet intensity. So that's the function that tells us where all the non-zero values of our wave packet are. And sigma x is the standard deviation of the actual wave function. So I'm going to use a different notation. Even though this is a standard deviation and that's a standard deviation, I'm going to use sigma x for the wave packet standard deviation and delta x for the probability distribution function standard deviation. All right. So now then we want to do the wave packet in k space. So what we're going to do is we're going to take the same approach. We know that the wave function, if we Fourier transform it, is going to have this form. So we've already did that in a previous video. So we're going to take exactly the same approach. We're going to calculate the standard deviation of the probability distribution with respect to k according to this expression. So we'll have to get this p of k, which we're going to get by taking this function and squaring it and normalizing it. That will give us our probability distribution function. And so the normalization of this guy we can do right here, and that comes out to be a squared square root of pi over sigma k. And then we calculate the mean value based on what we learned before, the same approach. So if I do that, that's going to come out to be 0 because our a of k was an even function. That's an odd function, so the product of even and odd is an odd function, so that's going to come out to be k. Exactly the same logic as before. And now we're going to do k squared times our Gaussian function here, and that's going to come out to be sigma k squared over 2. So I'm not putting in the explicit form for the Gaussian here, but that's just understood. I'm just trying to be a little more concise here. So finally then, we can plug this result into the expression for the standard deviation of the probability distribution with respect to k, and that's going to give us sigma k over the square root of 2. So as before, again, this delta k is the standard deviation of the intensity, so in other words, the square of the wave function, or the probability density, and this sigma k is the standard deviation of the Gaussian wave packet, okay? The amplitude, the a as a function of k function. So, taking these two results then, we have our result for delta x and our result for delta k. We multiply them together, and we get that is equal to sigma x, sigma k over 2. And in the previous video, we learned that sigma x was just simply 1 over sigma k for our Gaussian. And so we see for the Gaussian that we get the result of delta x, delta k is equal to 1/2, okay? Now, that's the smallest this product will ever be. So the Gaussian wave packet is the packet with the minimum uncertainty. So whatever your width of delta x is, then you can have the smallest possible delta k in order and get this product of 1/2. Any other wave function, then we know that, for example, we learned that the Fourier transform of functions that aren't Gaussian are not going to turn out to be of the same form. So, for example, a square pulse is going to Fourier transform to a sinc shape. So a square packet, wave packet, will turn into a sinc packet. And there are all kinds of other Fourier transform pairs, but Gaussian is the only one where you get a Gaussian after you Fourier transform Gaussian. So, generally speaking then, this will only be true for the Gaussian, but in general, for any wave packet with arbitrary shape, it will be greater than 1/2. So this product of delta x, delta k will be greater than 1/2. So this is what's called the uncertainty principle between wave packet position and wave number. Okay? And what we find then, of course, is that the more localized the wave packet is in space, then the greater the uncertainty in the wave number. So if you had a wave packet that was almost a delta function, so in other words, it was just very, very narrow region of space in which the wave was concentrated, then that would imply that you needed a very large range of wave numbers to localize it to such a small region of x. Conversely, if it was the other way around, if you had a very small number width of k, then you would end up with a large uncertainty in position. And this should make more sense to you if you think in terms of, say, a sinusoid. A sinusoid oscillation is just going to be a single k because it has only one wavelength. And if you think about what its k value is, well, there's just one. But if you think about what its position is, well, it extends from minus infinity to plus infinity, so it's over all possible values of x, so the width of delta x is effectively infinity, right? So if delta k is 0, meaning you have a sinusoid, then delta x goes to infinity. So that's another way of how the uncertainty principle is all consistent with what you know about trying to localize the packet. If you localize it in x, then you increase your uncertainty in k. If you localize it in k, you increase your uncertainty in x. All right. So this is the uncertainty principle for position and wave number. You could use the exact same arguments for the time and frequency. So we've already seen that there's a Fourier relationship between position and wave number. There's also a Fourier relationship between frequency and time. And so there's a similar uncertainty principle that is delta omega delta t is greater than or equal to 1/2 also. Okay. These two uncertainty principles will be, they're going to be important in classical wave equations, but they're also going to be very important when we get to quantum mechanics. Okay, so next what we're going to talk about is dispersive waves. And we've already seen sort of that a wave, if you actually had a real medium, not an ideal medium, and I created like a wave packet by, like, say, a rope. If it was a stiff rope and I did a wave packet, this wave would move across the string. If you did this in practice and you watched that wave, you would see that the wave would actually start to spread out and broaden as it moved across the string. That process, that broadening, is what's called dispersion. Okay? And we've learned that in the first part of the class, this chapter, that the omega over k is equal to a constant, which is the phase velocity for the wave. So if you have a wave with a given oscillatory frequency and time dependence and a given spatial oscillation, k, then that ratio is equal to the phase velocity for the wave. Now, some cases, if we get to go from ideal media to real media, we find that this ratio is not identical for all values of k. So there's a dependence of the phase velocity on the wavelength. And this is what happens in real media. So the consequence of this is that if you start out with, like this example, a Gaussian wave packet, as it moves forward in time, and this is what you would see if you did a pulse on a rope, then you would see that this wave pulse would move out and it would start to broaden as it shifted along, moved along the rope. And that is what's called dispersion. And the way we think about this is in terms of a plot of omega versus k. So ideal media has a linear relationship between omega and k, and that slope is the phase velocity. But what we have in real media is that some media will have this behavior where the dispersion relationship, the relationship between omega and k, will deviate from this ideal behavior, so that you get a smaller omega as you increase k. This is what's called normal dispersive media. There's another type of situation, which is called anomalous, where as you increase k, the frequency actually is higher than what you get in an ideal media. So generally speaking then, when you have normal dispersive media, the phase velocity is going to decrease. It's going to be smaller than what you have in an ideal media, and in anomalous media, the phase velocity will be higher than what you have in ideal media. Some examples of the different types of dispersion relationships you can have would be here, for example, this is a wave on a stiff string. So if you have a string that's really stiff, it's not as flexible as you would like, then what happens is that stiffness can actually cause your relationship between omega and k to become nonlinear. And this nonlinear behavior is what leads to dispersion. So this is an example of anomalous dispersion. Here you see the omega squared is equal to the square root of the tension over the string mass density, and then times k squared plus this extra term, alpha times k to the fourth. Alpha is a measure of the string stiffness. So if alpha was 0, then you'd go back to a linear relationship between omega and k. But as alpha goes to non-zero, then you have this nonlinear term that comes into play. Similarly, another example would be capillary waves that are traveling along the phase boundary between two fluids. So where two fluids meet, you can have wave behavior where the dispersion relationship is given by this expression, where omega squared is proportional to k to the third power, and the proportionality constant is the surface tension divided by the density of the heavier and lighter fluids here. So this is a nonlinear relationship which leads to dispersive behavior for the waves. And another example, the final example here, is that light also, when it's traveling in matter, can be dispersed. So what you find is that the dispersion relationship is omega is equal to c naught, which is the speed of light in a vacuum. Then it's times the wave number, then it's divided by this function that's called the refractive index. So this n of k depends upon k, and when this comes in, it has a nonlinear dependence on k, and so this whole expression, this whole dispersion relationship is nonlinear, and that's what leads to dispersion of light. And that's what you're seeing when you see, for example, white light shining on a prism and it being dispersed out, spread out into the different colors of the rainbow. So this is what we need to understand, for example, why laser light, which can travel very long distances, never disperses. And think about that, but we'll come back to this in a bit. But a laser, what's special about laser light that's different than white light? White light will disperse, but a laser light won't disperse. So if you look at a plot of omega versus k, again remembering that we have ideal media where omega is equal to k times the phase velocity, and that's constant, same for all k values. Real media will deviate away from this, and so you see that if I start here at the origin, that the slope depends upon which k that I'm looking at. So if I'm looking at k naught, then I have this slope, which is a different phase velocity than I would have if I was in the ideal media case. And if I went to another point on this line, so if I say went to this k, you can see here, if I go up to here, the slope from the origin to there is a different value than it is to here, or likewise to there. So everywhere along this line, if you go from the origin out to any point, you have a different phase velocity, whereas if I'm on ideal media, all k's have exactly the same phase velocity, the same slope. So this is one of the reasons why you can see that, like if I have monochromatic light where there's only one wavelength, then the light will travel through space with one phase velocity because there's only one wavelength. But if I have multiple wavelengths, then I'm going to see multiple phase velocities in my wave that's moving. So whether it's light or any other wave, and in this case light is a dispersive wave. So if you have just a single wavelength traveling, then you'll have only one phase velocity. But if you have multiple wavelengths, then you'll have multiple phase velocities. So this explains then why lasers are monochromatic waves which have only a single wavelength. That's why you won't see dispersion behavior, because they actually only have one phase velocity present in the wave. And we'll come back to this a little later. So when it comes back then to dispersive waves, and you have a wave packet and you have a range of wave numbers, take for example here, let's say I have a wave packet that's centered on a particular k naught value, and there's a range of wave numbers that compose that wave packet, then you see that inside that wave packet, if I start from the origin and go out, that there's very different slopes. These dashed lines represent different slopes, represent the different phase velocities that wave has, all right? So how are we going to describe this wave moving through space when we have all these different phase velocities? So what we're going to do is we're going to do a Taylor series expansion. Go back to that particular case here. Since we know all of our waves all the waves that, the sinusoids that make up our wave packet have k's that are in this range here, centered on k naught, let's do a Taylor series expansion about k naught. So we're going to evaluate omega as a function of k. We're going to do the expansion about k naught. We're going to take the first derivative at k naught times the deviation from k naught. The second derivative, 1/2 times the second derivative, evaluated at k naught times the deviation squared from k naught, and so on. That's our Taylor series expansion. And we're going to define the first derivative as this quantity that I'm going to use the symbol Vg for to represent something called the group velocity. And this term here, I'm going to use the symbol alpha to describe the second derivative term, which is also going to be helpful when we get to learning about how the wave actually disperses. So taking this expression here and using my new definitions, I have this series expression. And what I'm going to do then is I'm going to take this expression here, and I'm going to go back to my wave function, and I'm going to do a substitution for omega to try to get it in terms of Vg and alpha and so on. So let's just start simple. Let's take our expansion for the dispersion relationship. So here's omega naught. So if it was purely ideal media, then we wouldn't even have this term, and it would just be omega naught omega k would just be equal to omega naught. But now in this case, we're going to have the first correction, which is Vg times delta k here. And I'm going to take my expression for a generic wave, which has some distribution of amplitudes as a function of k, and it's all going to be moving through space with this time dependence, integrated out to give me my wave function as a function of position and time. And I'm going to substitute in for omega here, and that's going to give me this expression right here. And now I'm going to do a little math, and I'm going to rearrange this to describe it instead of in terms of k, I'm going to describe it all in terms of the deviation of k from k0. And when you do that, and I'll leave this as an exercise for you, you can take this expression here and write it as the product of two terms. One is a simple sinusoidal wave, which is moving with k naught and omega naught. So that's the center of where our wave packet is in our distribution of k's is centered on k naught. That's going to be a sinusoid, but it's also going to multiply times this part of the wave function, which is going to give us the shape. So this a as a function of delta k. So this is describing the amplitudes as a function of delta k, times this part here is going to describe a wave shape that's moving through space at a velocity of Vg. So that's the group velocity. So we have then, in this shape, we have a phase velocity, which is here in the sinusoidal part, and then we have a group velocity, which is here in the wave shape part. So we're going to make these ideas a little clearer here as we go to look at some simulations later. But let's just make sure that we fully understand then what we're learning here. So what we see then is that for a wave packet, which covers a range of k's centered on k naught, that the group velocity of this wave packet is the derivative evaluated at k naught of the dispersion relationship here. So that's this slope right here. And the phase velocity comes from the origin out to each one of these points. So the phase velocity of this wave, the sinusoidal part, is the slope from the origin out to where k naught is. So you can see those guys have different slopes. So this slope of my pointer here is Vp, that's the phase velocity, whereas the tangent at that point, that's Vg, that's the group velocity. So this is where we'll look at some demos, some little simulations here. I can pull these up here. Whoops. And give me a second here. Grab the window. Okay, here we go. All right, sorry about that, for a little while. Okay, so now I'm going to start with the first video, which is, I'm going to restart it here. Okay, so this is a video where we see an example of a group velocity faster than the phase velocity. So what's happening is we have two waves that are added together, which have different phase velocities. Now remember, in ideal medium, these guys would have the same phase velocity, but here they're different. So when these two waves add together, we get a train of wave packets. And when this finishes moving all the way over here, he's going to show us, they're going to show us in this video, the phase velocity and the group velocity. So remember, the phase velocity dot is just the dot that stays on top of the wave crest and moves. Whereas the group velocity is the wave packet, so here's the train of wave packets, and that's the velocity of the shape as it's moving through here. And we move on to the second one here, so you can see. And here we have an example where we have zero group velocity because our three waves that we're adding together all have exactly the same phase velocity. So this would be the case of an ideal medium where the phase velocity is identical regardless of what the wavelength is. And you see when these guys add together, we get a wave packet, but because the phase velocities are identical, then you'll see that the group velocity is 0. It doesn't change. Whereas the phase velocity is moving forward with the same speed as each of the individual ones are moving forward. Now let's do the third case here. And in this case, we have 3 waves traveling added together, but they have slightly different phase velocities. So as you see, as they come together and make a train of wave packets here, that the phase velocity is moving forward, but the group velocity is, for the wave packet is moving backwards. So here we have a case where we have a negative group velocity and a positive phase velocity. Okay, and that was example 3. Let's look at example 4. So this case has 2 waves which have equal but opposite sign for their phase velocities. So when you add them together, the average phase velocity is 0. But you can see that when these come together, even though the phase velocity is 0, they'll come together to give you a positive group velocity. So we'll get a train of wave packets with a positive group velocity, but the phase velocity will be 0. So let's watch as these 2 guys get fully added together, and we'll get the full train of wave packets. And so here you see it. And here you see the phase velocity not moving at all, because this is equal and opposite. Added together, there's 0 phase velocity. But the group velocity is moving at a pretty steady clip as the wave packet train moves here. Okay, and then that was the 4th example. Let's do the last example here. And in this example, there we go. In this example, we're going to have 2 different phase velocities, and the result here, when these 2 add up together with different phase velocities, wait and see here. So we're getting our train of wave packets, and let's wait here. And here we see the group velocity is negative, while the phase velocity is positive. Okay. All right, so the point of these videos then is to really just sort of help you understand that the difference between the concepts of group and phase velocities. This will be important down the road as we learn about the use of wave mechanics and quantum mechanics. And so we want to get these concepts out of the way. All right, so let's move on then to the last bit of this section on dispersive waves. Is that so far we've been looking at this idea of group velocities, and we've looked at our series expansion where we stopped at the group velocity and we left out that alpha term, which that alpha term, if we include that term, that's going to give us the wave changing shape. So far we left out the alpha term, so our waves will have a group velocity, but they will maintain their shape as they move through space. It's only if you add in the alpha term that they will broaden out as they move through space. So what I'm going to do is I'm going to take my expansion of omega with respect to k, my Taylor series expansion, and if I include the alpha term, and I'm going to leave out the derivation here, but this is the result, I still get the sinusoidal part here, but now I get a part where it looks like this, where now I have an alpha term, delta k squared times t divided by 2 added into the exponent here. So that's, it gets starting to get a little complicated. So what I'm going to do is just take the one example of a Gaussian wave packet. So if I go back and I get the distribution of k's for a Gaussian wave packet and plug that analytical expression in here and do some math, I can get an expression for the intensity of the wave, so the wave function squared, that looks like this here. So this is, again, a Gaussian. So here's a amplitude factor here, which you can see is going down with time, because this term is getting bigger with time. And then you see the shape over here, which is also has a time dependence, which we had before, but now you see in the denominator, what would normally be in a Gaussian, the variance is this big term here, which is the overall variance of this guy. So what we're going to do is we're going to take this guy, we identify that as the square of the standard deviation. So I'm going to write that out here, take all of this here, rewrite it here. This is the standard deviation of the wave, which is equal to the original time equals 0 standard deviation of the wave times the square root of 1 plus alpha squared t squared over delta x naught squared to the 4th power. So that's the wave intensity. So this is the probability amplitude, how it's moving in time, and this is what the standard deviation is doing. So you can see it's getting bigger and bigger as time increases. And that explains then, taking that to the next slide here, this is the expression we derived for a Gaussian shape, why a Gaussian pulse shape, as it evolves forward in time in a dispersive medium, is going to broaden out like this, with this expression here. So you have to include the alpha term in order to see that. So this is moving with the group velocity, and it's broadening out with this alpha factor in this expression here. Okay, we're gonna stop there, and then in the next video we'll start looking at 2 and higher dimensional waves.